right, so here we have the notes for section 1.7, deals with modeling with functions. So the first one we got here is functions from formulas. So it says write the area A of a circle as a function of its radius, its diameter, or its circumference. So radius r is probably the one you're most familiar with. So A equals pi r squared, so area of a circle in terms of its radius. Diameter, now remember that the diameter is equal to twice the radius, so r is equal to d over 2, so which means I can replace the r in this equation with the diameter equation, so pi d over 2 squared, which would become 1/4 pi d squared. So square that, that's where the 1/4 comes from, the 2 on the bottom, and then d squared stays d squared. There's circumference c, so circumference is 2 pi r, but I need to solve that for the radius. So the circumference divided by 2 pi is the radius, and then that goes up into this equation. So the area is equal to pi, and then circumference over 2 pi squared. So pi times c squared over 4 pi squared. So that's just squaring the fraction. So this is going to cancel that guy. So I'm going to have c squared over 4 pi. So it's the area in terms of the circumference, area in terms of the diameter, area in terms of the radius. Okay, so example 2, a square of sides x is cut out of each corner of an 8 by 15 piece of cardboard, and the sides are folded up to form an open top box. So we've got a piece of cardboard. We're going to cut corners out of it, and each corner is x by x on the cuts, and each side, that's 8, and that's 15. So write the volume. So what's going to happen is this is going to get folded up into an open top box that looks something like that. Now, we need to figure out the dimensions here for this box. So when you cut, you're going to fold on these longer dashed lines here. So this front edge was the 15, but I cut 2 corners out of it. So it's now 15 minus 2x. This side going back was this piece, which was 8 inches long, but I cut 2 corners out, so it's 8 minus 2x. Now the height of the box is actually x, because when these cuts get folded up, this piece here, these smaller dashed, they become vertical, so they're the height. So the volume of the box as a function of x is length, 15 minus 2x, times width, 8 minus 2x, times height, x. So then it says find the domain of v as a function of x. So what this is saying is that what's the size cuts you can make? Well, 0 is the smallest cut you can make, and then x. And then the biggest cut you can make is actually 4 inches. The reason it's 4 is that if you look at this side, your short side, if I cut in 4 inches from either edge, I cut the whole side off. There's nothing left to fold up. So you can have a less than here, but you cannot have the or equal to's, because if you put an equal to bar underneath, that means you can make a cut of 0 or a cut of 4, which isn't allowed. It has to be slightly more than 0, otherwise you can't fold it, or slightly less than 4, otherwise you cut the whole side off. So that's inequality. As an interval, it would look like this, an interval notation. Okay, so third one says graph v of a function of x over the domain and use the minimum or maximum finder in your grapher to determine the maximum volume such a box could hold. So let's see if we can get my screen to show up. Menu, graph. So I need to graph that equation, 15 minus 2x, whoops, and then 8 minus 2x, and then x. Draw. So kind of hard to see. So I'm going to do view window. No, I'm going to do zoom. We'll say, let's try auto. Where'd it go? Auto. There it is. So it's zoomed way out now, so it looks like this. But it says on a Casio, if you want to find the maximum value, you can press G-solve and then hit max, and it will find the maximum value for you. So there you go. Determine the maximum value such a box could hold. So since V is acting like my Y, V is equal to 90.7 cubic inches. The X is how big the cut should be, 1.66666. Oh, right here. That's this part. X equals 1.6, we'll call it 6.7. It's not 1 2/3 because that 6 doesn't keep repeating. It does eventually 7, 9, 4, so on and so forth. But that value gives you the maximum value for your box. If you cut about 1 2/3 in from each side. All right, functions from graphs. So it says a small satellite dish is packed with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter, 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. How tall must the cylinder be to fit the middle of the dish and be flush with the top of the dish? So I'm actually going to do this guy upside down. So there's my satellite dish. So it is 24 inches wide. It is 6 inches deep. I'm going to put into it a cardboard cylinder to support it. And it's 12. The diameter is inside here is 12 inches. Okay. So here's my lovely equation or picture. I need to figure out the equation that's going to give me this. Now, I'm going to drop in a set of coordinate axes. Looks like this. So this point here is going to be at 0, 6. And I want this piece over here. Now for this parabola, I actually know a couple locations. I know this point over here is at 12, 0. This point over here is at negative 12, 0, because the whole thing has to be 24 wide. So this point is 6, I don't know. And this point over here is at negative 6, I don't know. But the y values are the same. So I need to figure out the equation of my parabola so that I can plug 6 into it in order to find, what am I looking for? Yeah, in order to find the values there. So the equation for a parabola is a quadratic, y equals x squared plus bx plus c. It looks like this. So what I need to do, essentially, is make a bunch of equations to solve this, because I know some x, y values. I actually know c already. C is 6. It's going to be that number right there. And actually, there's a better formula to use. Ax minus h squared plus k, because this is the horizontal vertical transformation. So h and k are the vertex, so this is y equals some value x minus 0 squared plus 6. So my generic equation actually just looks like this. The b value is 0. And to figure out what a is, I can use any of these points to find the value. So we're going to use 12, 0. So 0 equals a 144, so that's 12 squared, plus 6. So subtract the 6 across, divided by 144, and that is my a value. So negative 6 over 144 is negative 1/24. And now, let's rewrite my whole equation. So y equals negative 1 over 24, x squared plus 6. So if I check my x values, if I plug 12 in, I should get 0. 12 squared divided by negative 24 plus 6 is 0. So this is the correct equation. So now I know my x's are 6 or negative 6, so I'm going to plug 6 in for x and figure out the y value that goes with it, because that'll be how tall the thing has to be. So this is negative 1/24 times 36 plus 6, and all that can go in my calculator. Negative 1 over 24 times 36 plus 6 is 9/2, so with a decimal, So y equals 4.5 inches. That's how tall the cardboard has to be to rest, in there comfortably. Okay, 4, grain is leaking through a hole in the storage bin at a rate of 8 cubic inches per minute. So we'll write that down, 8 cubic inches per minute. The grain forms a cone shape on the pile below. As it grows, the height of the cone remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? So we've got a cone shape. That's the radius. That's the height. So let's see here. Volume for a cone is 1/3 pi r squared h. But it says as it grows, the height of the cone will always remains equal to its radius. So I can make all of these h. So the cone is 1 foot tall now. How tall will it be in 1 hour? Okay. So okay. Sorry, I had to think about it. So I get 8 cubic inches per minute. So I need to convert that into cubic feet per hour because I'm measuring my time in hours and my cone is 1 foot tall. So 8 cubic inches per minute. So there are 60 minutes in 1 hour. This is some unit conversion. Cubic inches in a cubic foot. So 1 cubic foot is 12 times 12 times 12, or 12 cubed, 1,728 cubic inches. So 8 times 60 divided by 1728. And this comes out to be about 0.28 cubic feet per hour. So in 1 hour, I will gain 0.28 cubic feet of height. So right now it is 1 foot tall, so I need to figure out its volume, add that onto it, and then solve backwards to get it. So the volume equals 1/3 pi, because r is 1, and so is h, because the cone is 1 foot tall now, and the height is always equal to the radius. So this is 1/3 times pi, which is about 1.05 cubic feet. So 1.05 cubic feet plus how much I'm going to gain in an hour. So this is 1.33 cubic feet, and then work backwards. 1.33 is equal to 1/3 pi, and instead of r squared h, I'm just going to put h cubed, because r and h are all the same thing. So 1.33 times 3 to cancel out the 1/3, divided by pi to cancel out the pi. So the height is about 1.27 feet, if you notice. So there we go. I gained about that much. Okay, example 5, how many rotations does a 15-inch radius tire make per second on a vehicle traveling 70 miles in 1 hour? Okay, so I need to figure out the circumference of this guy. So the circumference is equal to 2 pi r, so that's 2 times pi times 15, so that's 30 pi, which is about, actually we'll just leave it as 30 pi. So that's the circumference. I go 30 pi inches per rotation. So let's see here, per second on a vehicle traveling 70 miles per hour. So I need to figure out what 70 miles per hour is in inches per second. So 70 miles per hour. In 1 hour there are 60 minutes. In 1 minute, there are 60 seconds. In 1 mile, there are 5,280 feet. And in 1 foot, there are 12 inches. Okay, so 70 times 5280 times 12, the numbers across the top, divided by 60 across the bottom. So this is traveling at 1,232 inches per second. So, and I get 30 pi inches for every rotation. So 1,232 inches per second. And it takes me 30 pi inches per rotation. So the inches are go on bottom so they can cancel, because I want rotations per second. So divided by 30 pi, and I get 13.1 rotations per second. So there we go, some fun unit conversion. Okay. 40, okay. Lastly, functions from data. So what this problem is having us do is generate a function y that approximates the high temperature as a function of the low temperature. Use this function to predict the high temperature in May for Madison, given that the low was 46. So in general, what you need to do is you're finding the line of best fit. So it says make a scatter plot of the data points. The points do not need to pass the vertical line test. Determine from the shape of the plot where the points seem to follow the shape of a line, parabola, cubic, sine, so on and so forth, and then transform the basic function so that it matches. So I'm going to do this really, really rough and find the lowest low and the highest low and use those as my two endpoints and just generate a line that connects the two. It's not necessarily the best way to do it, but without technology, it's kind of the best way to do it. So the lowest low, let's see here, there's 52. Is there anything lower than that? There's 50. Looks like that's the lowest low, so we'll use that point, 50, 70. And then I need the highest low. So highest low, there's 76. I don't see anything higher than that. So Miami, 76, 92. So I'm going to use these 2 points to write the equation of a line. So to write the equation of a line, I need 2 pieces of information. I need the point the line goes through, which I have 2 of them to use, and I need the slope of the line, which I can calculate. So y2 minus y1, x2 minus x1. So that's 22 divided by 26. So that's 11 out of 13 is my slope. Let's write the equation of the line. This is point slope formula. Looks like that. So y equals 11/13, x minus, now I can use either point, I'll use this one, 50 plus 70. So that's my equation. So find a function, and then use this function to predict the high temperature for Madison, given the low was 46. So that's my x value. So y equals 11/13, 46 minus 50 plus 70. And then all those are numbers, so I can all in my calculator at once. So this is, what's that, 16? So 11/13 times 16 plus 70 comes out to be about, it's 83.5, so we'll call it 84 degrees would be the high using our line. Now this is not the line of best fit, so it's a real rough approximation. Calculator or Excel or Sheets would be much, much better about finding the actual line of best fit for you. But that brings us to the end of this section. Thank you.